In this video, we're going to look at the cardinality of cosets. So to get started, we're going to let R be a ring and S be a subring of R. And we'll let A be any element of R. And I want to recall that the left coset of S, defined by R, is going to be A plus S, and that's simply the set of A plus little s's, where little s ranges through all of the elements of capital S. And there's an obvious question, and that is the cardinality of the coset the same as the cardinality of the subring itself? Because after all, we're letting this guy here range through all of the elements of S, and it looks like there might be a one-to-one correspondence between A plus S and just the little s's inside capital S. And so, in fact, that's how we're going to answer this particular question. So we're going to basically think about whether or not we can find, so can we find a one-to-one onto function? I'm going to call my function f, and I'm going to have it go from the subring to the left coset. So can we find such a thing? And I want to make a note that there is an obvious candidate. And the obvious candidate for this particular function is to simply let f of little s be a plus little s for every single little s inside capital S. Obviously, this is a function. It takes one particular element inside the subring to the element a plus s. And so the real question is whether or not this f is one-to-one and onto. So again, just to remember that our function is going from the subring to the coset is given by f of little s is equal to a plus little s for all little s's inside the subring. And I want to know, is f one-to-one? Now, it's important to understand that this f is not a ring homomorphism because the left coset is not a ring homomorphism. So we have to use the definition of one-to-one. There is no such thing as a kernel for this particular function. It is a function from the subring to the coset, but it is not a ring homomorphism. So we have to use the definition of one-to-one function. And the definition of a one-to-one function is that we look at f of two inputs, and we're going to assume that they're equal, and we want to see if that will imply S1 is equal to S2. So if f of S1 equals f of S2 implies S1 is equal to S2, then we can say f is one-to-one. So to start our examination of whether or not this function is one-to-one, we are going to assume that f of S1 is equal to f of S2. And I want to think about what that means. Well, our function is defined up here as f takes any element inside the subring to a plus that element. And so consequently, what I know is that a plus S1 has got to be a plus S2. And I want to think about this equation. This equation is an equation inside the ring R. And I know that that equation is true by the definition of our function f. But since this is an equation inside the ring R, we can certainly look at minus a plus S1 is equal to minus a plus S2 in the ring R. And of course, addition is associative, so I can put in those parentheses, and minus a plus a is just a big fat 0 inside the ring. And so we get this equation, that 0 plus s1 is equal to 0 plus s2, and that does indeed say that s1 is equal to s2, and hence we know that this function that is going from our subring to the left coset is indeed 1, 2, 1. So now the question becomes whether or not this function is onto. So let's look at that. So, is our function that goes from the subring to the coset onto? Now again, recall that our function is being given by little f of little s is simply a plus little s for every single little s inside the subring. And I want to also think about what onto means. F is onto happens if and only if for every b inside the target set, which in this case would be a plus capital F, there exists somebody inside the domain of the function, in other words, a little s inside s, such that f of that little s is equal to b. Now, the basic idea of what this definition means is we have to start with this kind of an assumption, and then we're going to have to figure out what s is. So to show that f is going to be onto, we're going to let b be any element at all inside our left coset. Now what that says is there does exist somebody, I'm going to call him S3, inside capital S, with b equal to a plus S3. Now look at this. F of S3 is a plus S3, but a plus S3 is equal to b. And so what we actually have now done is we have shown that if I take any b inside the left coset, a plus capital S, then there is indeed somebody inside the domain of the function s with f of that something being equal to b. And so my f function is now onto as well as 1 to 1. And what does that mean? That says f is a 1 to 1 onto function from the subring s to the left coset a plus s. And in set theory language, what that means is we can say that the cardinality of s and the cardinality of a plus s is exactly the same thing. Now, a couple of things on vocabulary. If s is a finite sized ring, so if the cardinality of s is some number k, where k belongs to the natural numbers, then what this is saying is that the cardinality of a plus s is also equal to k. But the nice thing about our proof is that this is going to be true even for infinite subrings. So it's also important to note that if S is a infinite set, so I need to write this how I want to write it. So if S is an infinite set, then we still have the subring's cardinality will be equal to the cardinality for every left coset for all particular elements inside my ring.